welcome. I am Paul Prenny. I am out of the University of Windsor. I'm part of SharpNet, and I'm one of the persons that provide support to all of you and those needing support with Compute Canada. So today I'm going to talk about hybrid MPI. I'm assuming that you already know about MPI or know of it and things like this. So do a little intro on what that is, and then I'll give everyone a nice starting place to go to work with hybrid MPI, should that be something that is of interest to you. Okay, so what is hybrid MPI? Hybrid MPI is combining MPI. So if you've got an MP or want to do MPI programming, or you need to, fine, that's MPI. And you want to combine it with some other concurrent programming models within the same program. So you've got your MPI program, or maybe you don't have it yet, but you want to use MPI. But let's say you already have existing code that uses threads or OpenMP or MPLTHREAD building blocks or CUDA or whatever. Okay, especially if you have existing code and that code that uses threads only runs on one computer. You know, number of cores on that computer, and that's it. You can't make it run across more computers or anything like that. And let's say that code, you don't really want to modify it. It's tested, it works and all this. You just need to get it to run over more computers in a cluster. Well, nicely, MPI can really make that a much simpler task in many cases to do. Than perhaps rewriting your entire program to use MPI, because then you'd have to rewrite it, test it, debug it, make sure it's correct, do all kinds of, that's a lot of work and a lot of programs. Okay, so that's a common use case. If you're starting from scratch, you could just write everything in MPI and not worry about it. If you are starting from scratch, you can choose to balance things with MPI and other models, and there's different reasons for that. But today's topic, I'm going to discuss in general. I'm not going to talk about pros and cons too much about this little niche thing over this little niche thing and that. If you do have questions to that effect, you are best to submit a ticket to support@computecanada.ca and explain what you want to do and what you'd like to try achieving with your research, and we will help you with those that specific need and deal with all the specifics in what you're dealing with. Now, MPI stands for Message Passing Interface, and it enables one to write parallel code. You can code directly in MPI with C, C++, and Fortran, but there are many other languages that tap into that as well, like Python and stuff. So you can program using MPI with Python, and there's other tools that sit on top of MPI to do things like Julia and things like that. So MPI is commonly used. Each MPI program, if you want to think of it, is composed of a number of processes. So most people think all these processes are programs, but let's not confuse them. If we have one programmer running and we are running, let's say, 5 things in parallel, those 5 things in parallel to MPI are called processes, and typically you refer to their rank with that. Okay, now those things running in parallel for MPI, the communication between them is done by passing messages back and forth. And MPI, what makes it very useful on any compute cluster really, is it's designed to take advantage of the high-speed interconnects between each computer that's in the cluster. So these are very high-speed interconnects, and there's different kinds of interconnects and different speeds and different hardware vendors, different API calls, different all this stuff, and nicely it's all hidden behind in the internals of MPI. So when you write an MPI program, you don't have to worry about that. And that's a very good thing. So if MPI didn't exist, you'd have to worry about that. You'd have to write all kinds of code using specific API calls for, say, the InfiniBand fabric or the Mellanox fabric or whatever kind of interconnects are being used. And all the stuff that MPI does, you'd have to partially code that as well, like topologies and all that stuff. That would be an enormous amount of work and a major headache for many doing research. So nicely, MPI hides all of that. So that's a huge advantage. Okay, now each MPI process can run on a different node, or if you prefer, computer. So these clusters are filled with all kinds of computers, and each computer, of course, has various CPU cores. Some of them have GPUs and things like this. Great. Well, each MPI process has the ability to run on a different computer within that cluster. Now, it might turn out that they all run on the same one. If you say, oh, run 4 processes, and they all run on the same one, fine. But all 4 could actually run on different ones than that based on the scheduler. So that's important. Now, in order for things to talk to one another on different computers, you need them to be interconnected. And you want high speed and low latency. And that's where these high speed interconnects come in. So if you've never thought of how these clusters work, imagine well, you can imagine your own computer. You have a network card perhaps in it. You could connect network cards between them, but that's going to be very good speed, but it's not going to be your high speed interconnects that, all these sites that have clusters pay top dollar for, so that you can get all kinds of performance. So you can think of these high-speed interconnects as very specialized network cards, but they're not connected to the internet. They're just connected to all the other computers in the cluster. Now, very importantly, for each MPI process, the address space, the memory you access, pointers and all this stuff, is separate from all other processes. And this is why MPI uses messages for communicating, because you just can't give a pointer to a memory address to another MPI process and say, access it and do stuff with it. That won't work. You have to pass a message instead, and that's because the address space is separate. So when you are doing OpenMP programming, pthreads, and a lot of other normal traditional kind of programming with multiprocessing just on one computer, say on your laptop or a little workstation or something you have in a small lab at your university, you will start off with a short, simple program and maybe create some threads. What is a thread? Well, a thread of execution is something that's able to be executed concurrently relative to other threads of execution. Now, normally when you're talking about high performance stuff, you'll say, oh, we're going to run this in parallel. But it's better to use the word concurrently. So we'll use that there because things are not always in parallel. Now, also threads are a construct that has an independent set of values for each CPU core's registers. So on a computer, when you have a thread of execution, and let's say you have 2 of them, in order for the thread to run properly, since your computer can switch which CPU core each thread's running on, by default that happens, and because it can switch, in order for things to run properly, each thread has it saves and restores, has the ability to have the data for saving and restoring the values stored in a CPU register. Okay, so CPUs have very high-speed memory registers. They're very important for the operation of the CPU, and there's a fixed number of them, and those values need to be saved and restored when a thread of execution changes its running state or which core it's running on. And this is something the operating system manages and things like that. Some of you might be doing high performance stuff and you have to manage that in your code. But unless you're doing whole node allocation and you already got working code that's decently parallel in that, worrying about that level of optimization for a specific cluster is not worth it. But that's what a thread is. It saves and restores those values. The operating system will do that typically, and it runs. Now, some threads are tied directly to hardware, like GPU threads. I'm generalizing here. I'm not going to go specifically into nuanced topics of GPUs, but those threads are tied directly to hardware. So you have exactly N threads available for that specific GPU hardware. Whereas the software created threads, you can have as many as you want. Obviously, the hardware to run them on, if you make more than the number of cores of hardware you have, then you know, you're time slicing or whatever. But there's different aspects of threads. The main thing to realize, a thread of execution is a more lightweight way of breaking up work so it can run concurrently, or typically we consider it running in parallel. So what's a process? Well, for simplicity, we'll say a process runs on a single node or a single computer. You run a program on your computer. That's a process. Okay, and it's scheduled and controlled by the operating system, how it runs. Okay, and each process can have one or more threads of execution. So if it's serial or single threaded, it has exactly one thread of execution. So if you've ever written a Python program, a C program, a Fortran program or whatever, and you didn't do anything special about threads, that has one thread of execution, the thread of execution it runs on, okay? If you did do something special with threads, then that's a parallel or multi-threaded program, and you have more than one thread of execution. Okay, now here's how it works. When you have a process, that process will say open a file, allocate memory, do all kinds of stuff. This is acquiring resources from the computer. So if you say allocate a gigabyte of memory, okay, the operating system will give you a gigabyte of memory if it can. Great, you get that. Now what is the way it works is the operating system allocates that to the process. Every thread inside the process has equal access to that, unless your programming language is really special and does stuff differently. Generally speaking, every thread in the process will have access to those resources. So memory is shared, all the resources like file handles and all that stuff can be shared and all this stuff. Of course, you got to do stuff when you access things in parallel, but we'll leave that aside for now. But everything is shared, okay, within the process. However, outside the process, nothing's shared, unless I have the last bullet there, there are special operating system calls, or sometimes with specialized hardware, you can share stuff, but let's ignore that because normally those are special calls. So everything inside the process is available to be used, nothing special. So if you have a global variable and you have 10 threads inside a process, that global variable, all 10 threads can read from that variable, no problem. Okay, now if you want to write stuff, you can get into problems, but they have access to everything. Okay, but outside that process, there's no access. Okay, so you might say, well, what is a program? Well, for the sake of our topic today, we'll say a program is made up of one or more interconnected processes. Okay, but it functions as a single entity. So you run it, and you know, it's like running when you run your job. You run your job, and hey, it runs all over the place. Great. If you have an MPI program, that's what it does, and that's interconnecting one or more processes. And you might have scripts, you might have other things. That is what a program is. So it's a distinction we make to talk about something, but it's easy to get these things confused. So that's why I mentioned what a thread is, what a process is, and what a program is. Okay, so hybrid MPI. Let's come back to this. So let's say you want to do some OpenMP programming, or say some OpenMP programming, and you need to use GPUs to do some deep learning stuff as well, and you want some MPI stuff, whatever. You need a mess of stuff, and you want to combine it. You can with MPI. very minor changes are needed, and we'll talk about that in a short bit. So MPI makes it very easy to communicate between nodes and computers. Fabulous. If you've already done MPI programming, you already know roughly what that is. Obviously, with anything, you can get very detailed and very technical and nuanced and all that. But at a high level, it simplifies things. You can scatter data across a series of processes, and wherever they're at, it'll move that array of data. You can gather, collect it back. You can reduce, so let's say you need to sum lots of data across a variety of processes, you can do that. You can broadcast data. Okay, these are some of the basic MPI calls that one first learns when you first learn how to use MPI. Great. But let's say now you want to leverage CUDA, or you want to leverage OpenMP and stuff like that. And it might not even be all your code or doing research. It might be code that gets passed down to you from previous people doing research in your research team or whatever. And you don't want to rewrite it. You don't want to do all that. Okay, well, you don't have to rewrite it. You can leverage all of them put together typically and achieve a lot of success that way. You might say, okay, why wouldn't I want to do hybrid MPI? Okay. Well, why MPI? I forgot this one mention. The one thing we don't want to do is you say, oh, I don't want to use MPI at all. If you don't want to use MPI at all, then you have to say, oh, if you need it to run over more than one node or more than one computer, you'd have to say, what is the interconnection fabric on this cluster? And every cluster is a little different. So you find out what that is, then you'd have to find out, okay, I need the programming libraries for this, I need the documentation for it, and then you got to write code to communicate over that fabric. Your development time will go through the roof, and that'll be a lot of work that's usually not worth it. For the vast majority of researchers, one does not want to do that. And then to make matters worse, change the cluster, or the cluster gets upgraded, maybe the fabric's different. And then you have to rewrite your code again. And this is totally not worth doing when MPI can take care of all of it for you. So that's a big reason to use MPI. A reason to not use MPI, well, if you're using, like, say, OpenMP code in a naive way, or pthreads code or something in a naive way, it's very easy to have all your threads idle when you're performing MPI communications. And you kind of don't want to do that. If you have each thread of execution using up one CPU core, and you have MPI calls sitting there doing stuff, and when they're doing stuff, nothing else is happening, then you got all kinds of CPU cores doing nothing, wasting time. Now, if the MPI calls are really fast, maybe it doesn't matter too much. But if they're not always really fast, or if there's various things, that might be a big problem, and you want to reconcile it. Okay. The other thing is, if you are already working with code that's very performant, and you're doing whole node allocation, there's a reason I say that. You want to do whole node allocation because you want to deal with affinity, data placement, cache coherence issues, all that, and you want to make your code as fast as possible for the cluster it's running on. Then that might be a reason not to use hybrid MPI. Okay. And overall, and there might be a long-term consideration too. If you got a program that combines CUDA and OpenMP and all this, and an MPI and this and that, the code overall becomes more complicated. It might be simple if you view it a certain way, but it is more complicated, and that might be more work to maintain and enhance over time. So maybe initially it gets you going, but maybe over time you'll have to plan for rewriting code. And the other thing I will emphasize here is always benchmark and review your design decisions concerning your code. If you're unsure, submit a ticket, ask for help, and we will help you do that. But you want to benchmark your code. You don't assume something runs faster because it's in parallel, or because you used one API over another, or that you use one compiler over another, etc. Do not assume, benchmark the code. Okay, so you want to write MPI code, hybrid MPI code. Now, if you're starting from scratch, my advice, start by writing sequential code that solves a problem, then parallelize it, and then you can, get that to work with your pthreads, OpenMP, TBB, whatever, or maybe it's the CUDA step for you, make it work with GPUs, whatever it is, get that to work in a simpler way first. Okay, and then you can wrap MPI around such once you get the parallel code working. And if you get each step working, what's nice is if you keep the sequential code sequential somewhere, then you have something to compare outputs against. You can pass the same input, get output. Obviously, it'll need to be smaller because it's sequential, it'll take longer to run, but you can get output and you can compare that to the other programs you write that are parallelized, because you should get the same output, notwithstanding maybe factors involving random numbers or whatever. So that's really helpful to do, to have that, because then you have something to reference for the correctness of the code and testing and things like that. Now, if you already have code that does stuff on a single node with threads and or CUDA or whatever, great. Maybe your task is just to wrap MPI around such. Every task is different, so I'm not going to go into details how to go about doing that. So if you've never done, you want to do this and you've never done MPI programming before, submit a ticket to support at computecanada.ca, and we'll help you get into that. Okay, but if there's already code that works, tested, debugged, is correct, etc., you don't want to rewrite, test, and debug all that code. You want to do the next thing because you want to get your research papers, etc. You don't want to spend however number of months or years, weeks, months, or years redeveloping old code unless there's a really good reason to do that. So normally MPI programs will have this structure. This is C code, but it's very similar in other languages. There's a call to MPI init on line 6. On lines 9 and 10, very commonly you'll say, hey, what is my process ID? That's called rank in MPI. And how many processes are there? And that's the size call. Okay, so this program outputs hello from rank, whatever it is, of whatever the size is. And then the last line of the program is MPI finalize. Quick aside here, not everyone reads all the particulars in the documentation. Rank 0, the main thread in MPI, the main process in MPI, rank 0, is the only one officially, according to the MPI standard, that is allowed to properly clean up after MPI finalize. So if you have special cleanup code to do, it should be done in the main thread. That's the only one that should call MPI finalize. And whatever thread calls MPI finalize, where there's various nuances, the cleanup code you need should goes after that in that thread. Now, there's various nuances of this, but I just want to mention that so you're aware of it. So if you're writing like a C and Fortran program, actually really any MPI program, you want to clean up in the main thread immediately after the finalize call. Okay. MPI does not guarantee that all the other threads get properly shut down. That's the reason for it. So if you've ever encountered weird things with cleanup, that's the reason for that. If you don't know what I'm talking about, don't worry. At some point, maybe you'll encounter that and you'll remember something. There are some rules about cleaning up after MPI finalize. Now, to make your program a hybrid MPI program, this program, basic MPI, is the same as the next program, except I took everything in between the init and finalize and put ... And I replace the init call with something different. So line 6 is really the only change. Okay, and you can see here on line 6, all the way down to line 12, I have code. Okay, so it expanded, yes. And then I just put ... in a comment and MPI finalize. So to show you the simple version of this. So now here's the idea. I need an integer. So I have this integer here. I called it MPI init provided. I didn't know what to call it. I just called it that. You can call it whatever you want. What we need to do is, instead of calling MPI init, we have to call MPI init thread. The first two arguments are the same as MPI init. The third argument is special. And the deluxe form of that is MPI thread multiple. Okay. And the fourth argument is the integer variable I declared on line 6. And what this call does is it sets that integer variable to a value. It'll be one of 4 values. It'll basically be the value that the MPI implementation supports. So I'm saying here, I want the I'll say the most convenient and easy to use MPI support of threads possible. And that's MPI thread multiple. Okay. So if I say that, fine, but the implementation of MPI I'm using on a specific cluster or whatever machine I'm using on may or may not support it. So the MPI init provided variable gets set to the value that's supported. Okay, you can basically use a less than and all that for the 4 values, which I'll talk about in a sec. And if it supports less than it, it will return, it'll set that variable to that value. So you can basically do an if statement saying, oh, if it supports this, great. Otherwise, I'm going to abort. Or maybe your code can handle more than one case, in which case you have a more complicated if statement and fanciness. Now, also important in this code is I open an error message to standard error. So you see the error message, great. Okay, but I also on line 11 call MPI abort, because you're running an MPI program and you're going across all these threads. Some people just say, oh, I'll just quit with an error code. But MPI abort will tell all the MPI processes to shut down. Okay, calm world, it will tell all the processes that were requested to properly shut down, and you won't get weird error messages and all that from each one. So you want to call MPI abort instead there, so it'll cause the aborting of the code. And that's important because if something's not going to run, you want your job to immediately quit to minimize the amount of time that gets that Slurm tracks for your job, or sbatch. If you don't like Slurm, that's sbatch when you run your job. Okay, so that's what you do. So it's really only one call, but you basically need an if statement after it. Okay, there's a question about thread multiple. That's on the next slide, so I'm going to talk about that. All MPI programs should have MPI finalize in them. You should not assume MPI abort quits the program at that point. The main MPI program will quit and will do a finalize and all that stuff, but just make sure your code always is finalized. Don't worry about getting all the details correct, but get good flow in your code. Okay. So MPI init thread has 4 values. So a basic MPI program does MPI init, not MPI init with the underscore thread. Well, the very first one, MPI thread single, is the same thing as using MPI init. Okay, so when they added MPI init thread, they made MPI thread single, and that's identical to using MPI init. So if you do MPI init thread with MPI thread single, there's no difference between using that call and just calling MPI init. Now, the following items all support multi-threaded things in different ways. If you're using OpenMPI version 4, realistically, and all the newer MPIs, realistically, MPI thread multiple will be supported. If you have to use older MPIs, you may or may not find support for all of these MPI thread multiple. It might be the funneled one and things like this. That said, whoever set up MPI on the system you're using could have chosen different settings. So your code does need to actually call init thread and check the value to see which one it is. So these are numerical values. MPI thread multiple is a larger numerical value than MPI thread serialized, and that's larger than MPI thread funneled, and that's larger than MPI thread single. So you can use the less than comparison like I did in my if statement in this slide. Notice on line 8, I have a less than. So if this init thread set this integer variable to something less than MPI thread multiple, my code, I didn't write my code to work with that. So I'm just going to abort, get out of here. That's what you want to do with your code. So whatever you're going to make your code support is what you're ultimately going to set here. So MPI thread funneled means that only the main thread, in other words, process rank 0, okay, can make MPI calls. No other thread can do that. Only the main thread, okay? And by the way, it's a programmer responsibility to make sure you do this properly. If you don't adhere to that, your code's going to compile, it's going to run, but it's probably not going to run properly, or it might crash or whatever, okay? So there's more responsibility when you choose one of these other options. MPI thread serialized means it's multi-threaded, but only one thread at a time can make an MPI call. So if you are using OpenMP, then you need like pound pragma OMP single, for those of you who know what that is. Or you have to use barriers, fences, locks, whatever, to serialize your MPI calls. Okay, and then an MPI thread multiple means it's multi-threaded and all MPI calls are thread safe. So that one's the easiest to work with if you have to actually call MPI from different threads and all that stuff, and you don't want to worry about all the details. Of course, you got to follow the rules for concurrent programming and use barriers, fences, locks, semaphores, whatever that you need in your code as is appropriate. So if you just want to have the easy way to make it multi-threaded, say MPI thread multiple, and you're good. But I believe all our clusters support that with MPI 4 certainly, probably version 3 as well. So MPI thread multiple can be used, and then you can just do your stuff and not worry about stuff. However, do the if statement, because if a value less than MPI thread multiple is returned, then it's one of the other values, and you have to adhere to that or make your MPI program quit. Okay, so when you pass in these values, notice it's the third argument here, you pass them in. Okay, so I put MPI thread multiple here, great. You might want a different value, you pass it there, and then that's what your program has to make use of. Now, when you get your program ready to run and all that, and you have, you maybe did SL lock to do some testing, whatever, all that, and at some point you want to submit your job, how do you organize your job? Well, you're doing a hybrid program. Normally with MPI, the CPUs per task will be 1. And you just say how many tasks you want. Okay. But when you're doing hybrid programming, what you want to do is the number of MPI ranks or processes will be the number of tasks. That's line 2 right here at the top. Okay. And the number of threads in each MPI rank you want to use. So if you're using OpenMP or some threaded library, the number of threads you have will be CPUs per task. Each of those threads will be assigned to a CPU essentially. Okay, so if you were to put 1 there, then your threads would multitask on 1 CPU core. So some of you might say, oh, well, if I set CPUs per task to 1 and each MPI rank has 2 threads, then what will happen is each MPI rank will run on 1 core. And due to the permission settings and Slurm and C groups and everything else, your threads will also run in the same core. they'll all be multitasking, time slicing on the same core. So if it was a total of 2 threads in total, then your time may well be double because it's running on one hardware core. So if you don't want your time to double and you want to have each thread running on its own core, then set the CPUs per task to, if it's for 2 threads, set it to 2, and then each thread will run on its own core. Okay. You will also want to set the memory per CPU option. You don't want to say just the memory. --mem is for everything, and you don't want that. Well, everything for the node, and that's not what you want. In this case, since you're fussing about CPUs per task, you want to say mem per CPU. Okay, so this way, you know how much each CPU is using for memory, and the scheduler will try to find available memory for that. And of course, say how long you need your job to run and any other options needed. You may or may not need to do module load OpenMPI. It's harmless to do it in your script, but you probably will want to set some environment variable or pass a command line setting to the program you're running so that it's set to the Slurm CPUs per task. This is really handy here because if you change this value on line 3, it will change the value being passed to your code. For OpenMP, OpenMP number of threads is the environment variable you set, and then you run it. Normally, you would use MPIRun if you're running on your own computer. On our clusters, remember to use srun. And you could submit this with sbatch-a, whatever your account is, and the name of the script. So it's almost like running an MPI job, except CPUs per task is not 1 anymore. It is some larger value because you have multiple threads and you have memory for those threads. So you're changing these 2 options. Now, if you're running on your own computer, sometimes, not all the time, you might need to use a special option, bind to. So if you're developing something, you're doing something on your own computer, it's common. I and many other people do this. It's just convenient. And you're using MPIRun. Okay, fine. OpenMP number of threads, you set that because you're using OpenMP, fine. But you discover that your program doesn't really run properly. You know, you're saying it should do all this multitasking or whatever, but it's not doing it, and your timings or whatever show up and they're not right. What you need to do is, by default, if you do nothing, MPIRun will assign each MPI process to a CPU core or to a socket or whatever, depending on your hardware configuration and stuff. So what you want to do is actually put --bind to space none, telling MPIRun not to bind the processes and threads to specific CPU cores and stuff like that. It'll just assign them to whatever. And on your own computer, this is very convenient. If you're using the cluster, Slurm has a wealth of options you can set if you need to get that level of control. Okay, so this does the same thing. 2 threads, OpenMP threads, NP number of processes is 3. With MPIRun, this will do the same thing as the previous sbatch scripts. 3 MPI ranks with 2 threads per rank. Now, that bind to thing is important. If you do benchmarking, and it should be in your code, you should see some speed improvements and all that as is expected. If you don't and you're unsure, submit a ticket to support@computecanada.ca and we'll help you with that, explain what your problem is and all that, what you're trying to run, and etc. And we'll help figure it out if you have to choose some special settings. By default, you probably shouldn't have anything to worry about. But I mention this just in case. I've noticed it from time to time where special options have to be passed in, certainly when using my own computer. On the cluster, things so far for me appear to be fine if I'm using the defaults, so I want to keep things simple using defaults. That said, you can run man sbatch or man slloc or man srun to see all the options for the Slurm commands. There are web pages as well that you can go to for Slurm to get that information. The bind to option in the man MPIRun page does actually say if you are trying to run things with threads in that, you probably want to use -- bind to none. Now understand that all of these tools allow you to assign CPU cores and CPU sockets and things like this to specific MPI processes and or threads. So this is called affinity and things like this. What you want to do at first, if you're just new to all this, use the defaults, go along with it, and then when you need to dive into more details, then you can deal with setting these things if needed. That said, I will say if you're running any threaded or a hybrid MPI program and you are not doing whole node allocation, the benefits of doing CPU affinity and all these other things is very minor, typically. So only if you're doing whole node allocation and you want to heavily optimize your code for one cluster, is this typically useful. Okay, so let's take a look at a simple OpenMP and MPI program. And this way I'm presenting this simply so you can easily like say, oh, I want to do the same thing. I'm just going to inject my code here and then learn some MPI on making your piece of code work better. Okay, so this part of the program is the same. Okay, same as what you saw earlier. So in this program, we'll get the com size and the rank. And here we'll do something very simple in OpenMP. We'll run this little segment between lines 21 and 25, the curly braces here. We'll run this segment in parallel. That's it. We'll just say hello from all of them. Okay, and then we'll finalize. So this is a very basic OpenMP program. This here is a hybrid MPI program, and when we run it, we can see how it'll run. So you can compile it, boom, and remember to pass your -f OpenMP option in. You have to use MPICC and do that. And then you can run it locally, or you can use sbatch or slloc. But instead of using MPI run, use srun instead. Okay. So now let's take a look at that. So I got code here. Click in the right window. Let's take a look. So this is the code I presented in the slides. And you can see here the hello from rank and all this stuff. That's normal basic MPI stuff. The hybrid MPI code does compile, it's just a check here. But the part I want to talk about right here is hello from thread 0 of 2, from MPI rank 1 of 3, and then hello from thread 0 of 2 from rank 2 of 3. So rank 2 and 1. So the order of these outputs will be arbitrary. Okay, hello from thread 1 of 2, okay, from rank 2 of 3. Basically, each rank will output 2 things. So you can see 1 of 3 occurs twice, 2 of 3 occurs twice, and 0 of 3 occurs twice. Okay, so that's how this is done. You may or may not need on your own computer bind to none. So if you wanted to run this OpenMP code, that's how you would do that. Okay. Now, just to show you, the bind to none is not necessarily needed. If you run it without, you may well see it runs, and you'll get different outputs each time you run it. Okay. So that's that program. This does run on the cluster. So if we come over to the cluster here, the job I ran this with is this. Okay, I compiled my program and I ran it as a job. And when it ran, because I'm getting 2 threads with 3 MPI ranks, that means I need 6 CPUs, and it's not instant. You have to wait a little bit of time to get that. So I'm not running it live in front of you. Once you get it and it runs, then the program outputs what it needs. So this is what's involved. This is what you want to see. You want to see these different numbers. And of course, if you're doing meaningful computations with them, then you can see they output with a certain amount of time involved. Okay, so now, speaking of benchmarking, I'm just going to show you a little example I had from my summer school demonstrations in the MPI course. Is if I take this C program that computes pi inefficiently, it's the classic pi problem presented in the Using MPI book and many other places on the web as well and all that. And I run it, but I benchmark it, but doing this OpenMP method and using OpenMPI as well. If I run it, I can do that, and nicely here, what I'm doing is I'm running it. I'm using 3 MPI processes with 2 threads in each process, and I run it multiple times. There's a for loop here, and each time I make it get larger, and I stop before it takes too long. Okay, so the idea here is I'm breaking down the work. So if I have 3 processes that take, I have the job and it's 3 processes, I'm going to have them do each n items a piece, and then I'm going to take the answers and send it back to the original. Now, when you do this, your code gets uglier. Okay, now you can separate out your code, but if you don't separate out your code, you'll wind up having code that looks more like my code here. So we come to the top, fine. Okay, now I wanted to write a function, so I wrote a function. Let's ignore it. Let's make my font a little bit larger and come down here and let's take a look. You can see what I presented to you is still there. So here's the beginning of my main, which you need in C and C++ and many other languages, although not necessarily called main. And here is my MPI init thread call. You need that. That must be the first MPI call you make in your code. MPI init or MPI thread, init thread. That must be the first call in your code. Okay, so that's the same as my slides. I get my rank and size. That's very common in MPI programs. And then if you ever want to benchmark an MPI, you just use the MPI wtime function, and it's a double value, and then you call it again and you subtract it 2, and that's how long it takes. Okay. And then you can do the number of intervals you want to process. Okay. Now, how you want to break it up. Do you want to have each thread do that many intervals, or do you want to have the program do that many intervals and break it up into each thread, depending on how you want to do it? In this case, I broadcast to all of the MPI processes the value of n. So I'm choosing and I'm telling each one to do that many iterations of this loop n value from 1 to this big number, which is 100 million or whatever it is. Okay, so I'm broadcast that to all of the MPI processes. Okay, so now what do I want to do? I come down here. Okay, I just assign some variable values and do some calculations. Great, to subdivide my interval up, because it's basically I have from 1 to 100 million or whatever it is. So I sent 100 million to all the threads. So now I need to find the first and the last index that I want to compute and things like this, whatever. And then I do OpenMP right here with this for loop. So this will cause this for loop to run in parallel. If you've never done OpenMP, don't worry. This right here just causes it to be done in parallel with threads, this for loop. Okay. And when done, I wind up with the value in sum. Okay. So then I'd use MPI to take the values of all the sums in all the MPI ranks. I want to add them up. Okay, these are doubles, and I want to sum them up. MPI double and MPI sum takes care of that. Okay, now this estimate of pi, you have to multiply by 4 because it's off by a factor of 4. So I do that, and then I output the value of pi that I get. And that's it. I basically output the total time, and finalize. Done. Okay, now it's the same procedure for other things you're doing. If you wanted to break up a job over a number of things and have a number of MPI ranks, and let's say each one maybe had to use a GPU or has to do a number of threads or a combination, well, you can break up your job to do that nicely over it. So that's the purpose of this talk. So we'll open it up for questions, and we'll go from there.